Bom dia, gente. Hoje temos a honra e o prazer de ter o nosso segundo seminário da Universidade de Helsinki. Acontece assim nessa era da epidemia. Hoje temos o Aleksi Vuorinen, que ele é do Helsinki, ele é finlandês, se formou lá e fez o doutorado lá, mas depois ele fez um postdoc no Instituto de Física Nuclear em Seattle, na Universidade Técnica na Viena, no CERN, pegou uma bolsa muito prestigiosa, que é a Sofia Kowalewska, da Fundação von Humboldt em Bielefeld. Eu conheci ele quando estava na Alemanha, e agora virou professor na Helsinki. Recentemente ele publicou esse trabalho no Nature sobre estrelas de nêutrons, que vai apresentar hoje. Como sempre, ele vai apresentar aos estudantes que precisam de assinar a lista de presença. Por favor, use o chat com seu nome e array. Depois vamos ter perguntas. Afterwards, there will be a question and answer session. People from Campinas have priority. But it's open to everyone. So without further ado, please, Aleksi, you can start. Everyone, please turn off your video and turn off your audio during the seminar, except Aleksi, please, for bandwidth reasons. Se a gente pode fechar o vídeo e fechar o áudio enquanto que Aleksi fala. Thank you very much. Aleksi, you can start.
Okay, thank you very much, George, and thanks a lot for the invitation. It's really a pleasure to be introducing our research to you guys. So, as George probably mentioned in Portuguese, what I'll be talking about is the possibility of having quark matter cores in at least some neutron stars. And this is some fairly recent work. It's mainly based on this third paper in my list, written together with Emeli Annala, Tyler Goda, Aleksi Kurkela, and Joonas Nättilä. But also it's partially based on some earlier work as well. One thing that I should probably mention already at this point is that if you want to read the actual paper, then please go to the Nature website, because we're actually not allowed to post the sort of up-to-date version of the paper on archive, and therefore there's an archive entry that has some relation with this paper, but it's sort of severely outdated. But it's an open access paper on Nature Physics, so everybody can certainly read it from there. So to start, somehow the motivation here is quite clear. We are QCD theorists. We are interested in mapping quantitatively accurately the QCD phase diagram. And as you all know, one of the special properties of QCD is its asymptotic freedom. And this asymptotic freedom implies, among other things, that if you consider QCD matter and you increase its energy density very much, then at some point you should encounter a phase transition, or perhaps a crossover, that leads you from hadronic matter to a completely new state, either quark-gluon plasma at high temperatures, or then quark matter at high densities. And this high temperature quark-gluon plasma, of course, has a long history, or its research has a long history, both theoretically. For instance, lattice simulations have shown that at high temperatures, the deconfinement transition is a crossover, not a real first order transition. And the sort of entire field of heavy ion physics is mainly motivated by the desire of creating this hot quark-gluon plasma and then sort of studying its properties. But if we then go to the opposite end of this QCD phase diagram to very high densities, or quark or baryon chemical potentials, and relatively low temperatures, then we run into the problem that it's very difficult to construct such matter in laboratory conditions, or even impossible one might say, but this does not mean that experimental or at least observational work would not be possible. We just have to work a bit harder. We have to look up towards space and try to find these objects called neutron stars that I will be talking about in this talk. And I would actually argue that there are lots of similarities between the study of heavy ion collisions and the physics of neutron stars. So these two are the only systems in existence in our current universe where we actually have QCD matter at very, very high energy densities, so high energy densities that one may actually be probing deconfined matter. In both cases, we're interested both in equilibrium, thermodynamic properties of the system, and in equilibration dynamics. That in the case of neutron stars refers to what's happening in neutron star mergers that we can probe using gravitational wave observations. And in both cases, due to the strongly coupled nature of QCD at moderate energy densities or energies, a first principles theoretical description really starting from the Lagrangian and computing everything in terms of Feynman diagrams, for instance, is difficult. And in both cases, to make sort of optimal progress, it's very important to also use observational or experimental input. And finally, even the ultimate goals in these two different branches of sort of QCD research are very similar. One wants to discover for sure deconfined matter. Of course, this has already been achieved in the case of heavy ion collisions, and not quite so with neutron stars. Then one wants to sort of measure and somehow deduce the properties of this deconfined quark matter or quark-gluon plasma. And finally, one would of course like to completely map the phase diagram of QCD, which is, however, a very, very tedious job, especially at high densities and low temperatures. But this talk is really about neutron stars, so let's first talk a little bit about those. The first thing to note when we are talking about neutron stars is that they are born as sort of remnants of old ordinary stars, so hydrogen burning stars. So when a sufficiently massive ordinary hydrogen burning star runs out of its fuel, it undergoes a very violent phenomenon called a supernova explosion. And what then happens to sort of the core of the old star is that it undergoes a gravitational collapse, which either ends up in the creation of a black hole or the creation of a neutron star. The neutron star is really quite a remarkable object. It's sort of it contains the densest matter that can be found anywhere in our sort of observable present-day universe, and it's the closest thing to a black hole that one can have. The most massive neutron stars are actually on the verge of collapsing into black holes. So in a sort of very crude approximation, one might even say that you can consider a neutron star as one huge macroscopic nucleus, atomic nucleus, because the densities inside neutron stars actually can reach and exceed the saturation density of nuclear matter, so the average density of a proton or a neutron. And from the point of view of a QCD theorist, the sort of main goal or main question to be answered is then that can we actually sort of determine the properties of very cold and very, very dense QCD matter somehow using observational information about neutron stars and ab-initio or first principles calculations. If these neutron stars are the unique place in the universe that contain this kind of super saturation density QCD matter, perhaps even deconfined QCD matter, and we are not able to sort of do first principles calculations to determine the properties of such matter, then perhaps it is somehow possible to use observations of astronomical observations of neutron stars to aid this process. Now, clearly here we have two very different worlds sort of merging. We have this macroscopic world of neutron stars, objects that weigh typically between 1 and 2 solar masses and whose radii are of the order of 12 kilometers or so. And then on the other hand, we have the microphysics of QCD, where we are sort of talking about length scales of order 10 to minus 15 meters or so. And the link between these two worlds comes actually from general relativity. It's the so-called Tolman-Oppenheimer-Volkov equations, these two that you can see here, that govern hydrostatic equilibrium inside neutron stars. So assuming that the star either doesn't rotate or rotates sufficiently slowly, which typically is a good approximation, then somehow these two differential equations hold, and they are both first-order differential equations, and they contain three unknown functions. So this capital M of R denotes the mass of the neutron star that's located inside a sphere of radius r measured from the center of the star. And then epsilon of r and p of r are functions, the energy density and pressure of the star, that are assumed to only depend on the radial direction, which holds true if the star indeed is not rotating. And then these two equations really govern the structure of the star, assuming that we know the relationship between the energy density and pressure, that means the equation of state of this QCD matter. Then we can solve these equations in practice numerically to obtain a unique mass-radius relation for the neutron stars. This mass-radius relation is the unique line on so a one-dimensional object on this so-called mass-radius plane that basically tells where all the existing neutron stars should lie. So in principle, if we knew the equation of state, we could just plug it into these TOB equations, and then out comes this one single mass-radius relation, a line on top of which all sort of accurate simultaneous mass-radius measurements of neutron stars, actually existing neutron stars, should collapse on. So this all sounds very nice and very simple, but unfortunately it's far from simple in reality. And the main reason is that the equation of state is a very, very difficult quantity to determine using sort of first principles machinery. In practice, historically, people have used different types of phenomenological models for sort of nuclear matter, and then what comes out are sort of wildly different predictions for the equation of state, and simultaneously widely different predictions for the MR relation. So this clearly shows that there is an sort of existing outstanding challenge that we are facing. And the main questions that I will then be addressing in this talk are the following. First of all, the best case scenario could be that if we are sort of clever enough, maybe we QCD theorists can actually one day predict this neutron star matter equation of state, and thereby predict the mass radius curve, mass radius relation, and just tell astronomers that look at your neutron stars, measure their masses and radii accurately enough, and then they will all sort of have to collapse on this one curve that we are giving you. Well, unfortunately, we are not that clever. So the next question then becomes, can we maybe use astrophysical observations to actually aid our theoretical calculations, and can we somehow infer the neutron star matter equation of state from using both first principles particle theory calculations and observations? And finally, the main question that I will be addressing in today's talk is, can we already at this point, given the current status of these kinds of calculations, make any predictions regarding whether deconfined quark matter should exist inside at least some neutron stars or not? Good. So then let's start our answering of these questions, or at least partial answering of these questions, from perhaps the most robust input we have, which is the robust theoretical limits of the equation of state that we know at this point. So before we go to the equation of state itself, one should note that what it really means is it's a relation between the energy density and pressure of neutron star matter. But there are many different ways of actually parameterizing this equation of state. we can, for instance, compute both the pressure and the energy density as functions of the baryon chemical potential, or as functions of the number density of baryons, the baryon number density, and then sort of infer the equation of state from these results. In either case, what one typically does is one sort of starts from the most dilute part of the star, its surface or its crust, where the sort of chemical potential is the lowest and the density is close to zero, and then one proceeds towards the center of the star, whereby the chemical potentials and different types of densities are of course increasing. And ultimately, one expects to not only reach this nuclear saturation density of about 0.16 baryons over Fermi cubed, but even go above it by a large factor, maybe by a factor of 5, maybe even more. And doing so, it's kind of clear or not surprising at all that also the composition of this matter changes dramatically. We start from individual nuclei or ions in a sea of electrons. Then the nuclei get more and more neutron rich when we go inside the star, and then at some point neutrons start dripping out of the nuclei. At one point one almost only has neutrons, and then in very deep in the core one could even have deconfined quark matter. But let's see how this goes. So this business of doing nuclear theory, trying to predict the equation of state, let's say as giving the pressure as a function of the baryon or quark chemical potential, this is a big field, and one has very well developed machinery that typically works the better the more dilute the matter is. So I won't be able to go into any details of such calculations, but let me just say that at this point the current status in this field is roughly that we know what's happening all the way up to nuclear saturation density, but not really above that. So the current sort of state-of-the-art ab-initio results from chiral effective theory, they predict the equation of state or the pressure to an accuracy of roughly plus minus 20% at around or slightly above the saturation density. But clearly this is nowhere sort of close to enough, because we know that in the centers of the most massive neutron stars, the densities reached are much higher. Actually, one can estimate that in this plot here, giving the pressure as a function of this quark chemical potential with a certain offset, the centers of different types of neutron stars are expected to lie somewhere around this region, which is clearly quite far away from where we can reach with sort of nuclear theory machinery. Now, fortunately, this is not everything we can do with starting from QCD. We also know that QCD is asymptotically free, and this alone implies that we know where this curve, the pressure as a function of chemical potentials, should go at very high values of the quark chemical potentials. It should, at some point at least, sort of asymptotically reach the equation of state of a system of free quarks. And this is what this dashed line in here is trying to show. Now the problem, of course, is that there is quite a big gap between these two regimes, and knowing somehow the asymptotic limit of the equation of state does not imply that we know how quickly or how slowly the actual physical equation of state approaches this limit. So then one could of course think of using standard tools like perturbative QCD, but here, at least naively, one might expect that those densities we are interested in neutron star physics, meaning sort of densities between 1 and 10 saturation densities, one might sort of assume that perturbation theories is not very useful, in particular because one doesn't even know in what phase of the theory one is residing. But perhaps, or I would like to at least argue that perhaps this is being too pessimistic. So we have a very similar situation that has been solved at high temperatures in the case of high temperature hot quark-gluon plasma. There we actually have a non-perturbative first principles tool, lattice QCD, that gives us the pressure as a function of temperature very accurately. And we also have resummed perturbation theory. And what has been shown from the work of a bunch of people, both using the so-called half-thermal loop perturbation theory and dimensional reduction and associated resummations, is that resummed perturbation theory, whose prediction is represented by this yellow band in here, it actually quite accurately predicts this high temperature equation of state or pressure down to temperatures only of the order of 2 or 3 times the pseudo-critical temperature of the deconfinement transition. And similarly, one might then also hope that something similar could be done at small temperatures and high densities. Well, the most important difference, of course, if we go to the realm of 0 temperature and high values of the baryon chemical potential, which is shown here, is that we now do not have a lattice prediction because of the infamous sign problem of lattice QCD. I wouldn't be giving this talk if lattice QCD worked at high density. Now this particular yellow band is from a 3-loop calculation by Aleksi Vuorinen, Paul Romachkin, and myself from 2009, and it does not contain any real resummations. So this is really sort of the prediction of unresummed perturbation theory. But we are currently working hard in thinking about whether one can improve from here. And indeed, at least in some sense, one can. We have very recently finished the computation of the first part of the for-loop pressure that's proportional to g to the 6 times log squared g, and we are almost there with also the next term, the linear log term at this for-loop term, this for-loop order of the perturbative expansion of the 0 temperature pressure. But even this 3-loop result actually turns out to be quite useful in these studies of neutron star physics. So if we take this yellow band from here and plug it into the previous plot, what we see is sort of the appearance of these green lines in here. And now we also understand why I had this kind of vertical dashed line, not only at 1.1 nuclear saturation densities, but also up here at roughly 40 saturation densities. This is the point where the uncertainty in these perturbative calculations for the pressure of cold quark matter becomes as large as the uncertainty of the CET calculations at 1.1 saturation density. So clearly we still have a wide region in between, but perhaps this convergence of the perturbative result is not quite as bad as one could have feared. So in conclusion, I would say that there is a sizable no man's land between these sort of well-controlled results at low and high densities, and there's quite some work to do, but nevertheless we have robust limits, well-known limits, both at low and high density. Now to go beyond this point, we have several options. We could use sort of phenomenological models from sort of nuclear theory, which is of course the sort of standard methodology in this field. We could maybe use some sort of more modern technology from holography, for instance. Or what one also can do is to sort of, if one wants to be as model independent as possible, one can just take these two limits and then interpolate the equation of state between or through this no man's land, and perhaps constrain the result using observational data. So in essence, allow the equation of state to behave in any way possible in this sort of no man's land, this long density interval, and then see what comes out when we constrain the result using neutron star observations. And probably it's not difficult to guess that this third option is what I will be doing in the remainder of this talk. But maybe this is a good time to pause for questions if there are any. please shoot. Or if not, I can also just wait until the end and answer your questions then.
Maybe it's better. Maybe it's better to do until the end. But if someone has something urgent, then please send a message to chat.
Okay, good. So if there are no urgent questions, then let's proceed. Now, if you want to go along this sort of interpolation road, then of course a very urgent question becomes, what do we actually know from neutron star observations? So now let's do a very short detour from sort of particle and nuclear theory to astrophysics. So here, the first thing to notice is that so far hundreds of neutron stars have been observed, and several tens of neutron stars have associated rather accurate mass measurements. So here we have a bunch of neutron stars collected by Jim Latimer and the corresponding mass measurements. And what is somehow particularly useful for the purpose of constraining the equation of state are two of these measurements. The two stars that have sort of relatively small uncertainty limits and that correspond to the heaviest neutron stars known at this point. So there are these two stars that are very well known, one observed by Demarest and others, and another one by Antoniadis et al., whose masses were both measured using the so-called Shapiro delay effect of general relativity, and they both sort of point towards the existence of stable neutron stars with masses very close to 2 solar masses, perhaps even slightly above that. And this is an incredibly useful piece of information, because alone the fact that we know that these 2 solar mass stars exist allows us to discard all equations of state that don't reach this horizontal line in this figure that's drawn at exactly 2 solar masses. Now this would alone, as you can see, allow us to, for instance, throw away a bunch of different nuclear matter models, or in our sort of interpolation approach, this will allow us to throw out sort of finite sized regions in the equation of state or mass radius planes. Now, of course, one could also hope to say something about radius measurements, and indeed there have been a bunch of simultaneous or attempts at simultaneous mass radius measurements of neutron stars, but here we are going into a much more challenging sort of avenue, and here uncertainties are inevitably quite a bit larger than in mass measurements. So for a long time it was thought that accurate radius measurements would actually not be possible for neutron stars, but in the last couple of years there has been quite a lot of progress in the observation of X-ray emission from neutron stars. And again, I'm not going to go to any technical details, but I will just mention that there are a couple of very nice simultaneous mass radius measurements that sort of predict the radii of a few individual neutron stars to an accuracy of plus minus 400 meters or so with 1 sigma error bars, or plus minus 1 kilometer or so from this very famous nicer observation. However, there are some systematic uncertainties, especially with these sort of more accurate X-ray measurements that are sort of not completely resolved yet. There are some groups that are saying that sort of rather large radii of the order of 12 kilometers or more are favored, and others who are claiming that the favored radii are of the order of 11 kilometers or less. And for this reason, we actually are not going to be using these radius measurements as input in our calculations, but rather later on I will be showing you comparisons of our predictions with these kinds of measurements. And then finally, when talking about neutron star observations, one of course cannot exclude talking about the famous gravitational wave breakthrough that was made by LIGO and Virgo already in 2017, when they saw a gravitational wave signal, the first ever gravitational wave signal from a neutron star merger. And since then, they have, of course, seen many more, and very recently, for instance, it was publicized that they had even seen a very exotic merger of two objects, where one is a fairly large black hole, and the other one is an object that should actually not exist, that seems to have a mass of the order of 2.6 solar masses, which is either by far the most massive neutron star ever seen, or by far the lightest black hole ever observed. And this is a very interesting new development, but certainly there are way too many uncertainties here in order for me to say anything educated about it here. But from just this first ever gravitational wave measurement alone, there, at least in principle, could be three different types of observational inputs. One is tidal deformability limits that are obtained in the in-spiral phase of the merger before the two stars actually touched each other. Another one is sort of simultaneous independent electromagnetic observations that are present or are expected to be present if there's not an immediate collapse of the system into a black hole. And finally, there's hope that one day at least we will also see the observation of the ring down part of the gravitational waveform, which means the part of the merger where the stars have already touched each other and the system is equilibrating towards either a larger neutron star or a black hole. But for sort of practical reasons, the fact that this ring down pattern has not been seen yet, and the electromagnetic observations carry all kinds of sort of uncertainties in their interpretation that we don't want to be sort of affecting our results. We want to be as conservative as possible. I will only, in the results that I will be showing to you, take into account this first type of input, meaning tidal deformability limits. So what are tidal deformabilities? So basically, a tidal deformability refers to this coefficient lambda in a relation that describes the magnitude of the quadrupolar moment of the gravitational field of a given neutron star in response to an external quadrupolar field, meaning the gravitational field that's originating from its companion star. And it has been shown in GR simulations, in numerical GR simulations, that the value of this tidal deformability lambda in certain dimensional units has a significant effect on the observed waveform, and hence LIGO and Virgo were able to give hard limits, or in this case 90% confidence limits for where the tidal deformability of a 1.4 solar mass star should lie, based on this one single neutron star merger observation alone. And just similarly to the maximal mass parameter of neutron stars, also this tidal deformability parameter is immensely useful for any sort of theoretical calculation of the equation of state, because this is a quantity, the tidal deformability of a 1.4 solar mass neutron star, that we can very easily compute given a single equation of state. So we can use these limits to discriminate between possible viable neutron star matter equations of state. Good. So now finally, after all this, let us get to the interpolation part. So how do we actually perform the interpolation, and how do we optimally combine all these theoretical and observational insights that I've been talking about so far? So this is a fairly technical part. I will go through this very quickly, just trying to sort of give you the essential flavor of what one means by these interpolation calculations. So the qualitative idea is very intuitive. We for the equation of state, here shown as the pressure as a function of baryon chemical potential, we have these low density and high density limits that we know that the sort of true physical neutron star matter equation of state has to respect. And in this no man's land in between, what we can do, for instance, is we can use our favorite sort of basis functions, for instance, piecewise defined polytropes, and then just generate large ensembles of equations of state that somehow smoothly connect these low density and high density limits. How we do this typically is that we divide this density interval, this no man's land, into several pieces, and then we assume a certain type of behavior for the equation of state in each subinterval. And then we generate huge ensembles of equations of state requiring things like smooth matchings to these low and high density limits, the continuity of the pressure and number density, with the exception of 1 point for the number density where we allow a first order phase transition. Of course, we also demand that the equation of state is subluminal, and then optimally or optionally we can also enforce these different astrophysical constraints. So what does this then lead us to? Now I will be showing a few figures from this older paper from 2018. So here we used so-called four tropes, so polytropes composed of 4 different segments in this density interval. We sort of automatically randomly generated about 200,000 viable neutron star matter equations of state, shown as these cyan bands here for the equation of state and the corresponding MR relation. And then we started taking different astrophysical observations into account. The sort of simplest or most straightforward thing to do is to simply discard all those equations of state that lead to MR relations that don't reach this 2 solar mass limit, this horizontal line here, and that immediately gets rid of a bunch of equations of state that are too soft at low densities and thereby lead to neutron stars that are where 2 solar mass stars would not be stable. This simultaneously also rules out very small neutron star radii. We, for instance, immediately then know that a 1.4 solar mass neutron star has to have a radius of at least about 10 kilometers. The next thing then is to take into account these tidal deformability limits that I mentioned. And this, on the other hand, very nicely cuts off the opposite end of the spectrum. This, the fact that we have a non-trivial upper limit for the tidal deformability of a 1.4 solar mass star tells us that basically that the radius of a 1.4 solar mass star cannot be too large and that the equation of state cannot be too stiff at low densities. So hence we are only left with this green band in here. And then one can continue, one can speculatively, for instance, look at what would happen if we had a radius measurement of 12.4 plus minus 4 kilometers. This corresponds to one of the X-ray measurements. But here there's actually a caveat. This is not quite physical. We just did this for purposes like showing this potential effect in talks. Here we actually assume that the mass of the corresponding star would be accurately known, while in reality, as if you recall this particular plot here, the mass is anything but accurately known. So here we just assume that the mass would be exactly 1.9 solar masses, and then we would see that only this kind of a sort of purple band would remain, or pink band would remain, both for the equation of state and for the MR relation. Very good. So what I have shown so far is that one can constrain the equation of state, but I haven't said too much about the existence of quark matter. So now let's finally get to the main point. So now we move to this very recent work that just appeared a few weeks ago in Nature Physics, where somehow the philosophy is, however, very similar to the previous calculation that I just showed you. What's different in this newest calculation of ours is that here we actually start the interpolation from the speed of sound. So we basically interpolate the speed of sound as a function of baryon chemical potential, assume that it has a piecewise linear form, but this is actually not a very sort of crude, or this is not an assumption that is not too strong, because we don't actually fix the intervals of density or chemical potential in the beginning, but we allow for very sort of sharp features and very different types of behaviors for the speed of sound. But then we integrate the actual equation of state starting from the speed of sound, and we do this kind of an interpolation calculation, but we classify now our results in terms of the maximal value of the speed of sound, that is, that the equation of state reaches at any density, and also in terms of the latent heat of the deconfinement transition, for reasons that will become obvious very shortly. Now you might wonder, why am I interested in a quantity like the speed of sound? And the reason is actually that historically there has been a very strong tension between two fields. On one hand, nuclear theory, sort of neutron star physics, where people have typically assumed, based on model calculations and the measured properties of neutron stars, that the speed of sound of high density nuclear matter or QCD matter in general has to reach almost the speed of light in at least some density. It has to go to very, very high values. In some calculations, it actually even exceeds the speed of light, but this is of course an unphysical feature. But at the same time, we know from other contexts, basically from particle theory, that in most known physical systems where we can compute the speed of sound from first principles, for instance from using lattice QCD in high temperature quark-gluon plasma, we know that in practice the speed of sound never exceeds the conformal value of 1 over square root of 3 times the speed of light. This is the value that the high density speed of sound also has to approach asymptotically at very, very high densities. So basically the assumption in neutron star physics has been that the speed of sound has very non-trivial behavior. It goes to some very high values at sort of somewhat above the nuclear saturation density, and then it has to sharply go down and then ultimately increase towards this conformal limit of 1 over square root of 3 in the quark matter phase. But this would probably happen in a very slow fashion, as predicted by perturbative QCD. But whether this is really the case in nature, that such high sort of speeds of sound are reached, is kind of not clear at all, I would say. And in fact, there have even been speculations about whether this 1 over square root of 3 conformal limit for the speed of sound might represent a universal upper limit for the speed of sound in any physical system. There's been, for instance, this very interesting paper from 2009, where it is suggested that 1 over square root of 3 would be a universal upper limit, kind of a speed limit for the speed of sound. Now what we did in this recent paper of ours is that we performed an interpolation calculation that sort of produces, for instance, equation of state plots very similar to the ones that I've been showing so far, but with the additional feature that we can ask the following question. What would happen if we knew that the maximal value that the speed of sound reaches at any density is less than the speed of light? For instance, we can demand that the maximal value of CS squared is 0.8 or 0.6 or 0.4, or even this conformal value of 1 over 3. And what you can see from this figure is that when we go to lower and lower values of this maximal speed of sound, the equation of state band gets narrower and narrower. And actually, if we somehow knew from somewhere that the speed of sound is really truly sort of bound from above by this conformal value of 1 over square root of 3, then we would from here already almost exactly know how the equation of state of neutron star matter has to behave. because only this dark blue band in here is allowed if we make this assumption that the speed of sound has to be below 1 over square root of 3. Now, this is not the only thing that we can observe from here, but there's also another very curious fact that you might argue has been visible in our results already before. And this is the fact that to a fairly good approximation, this equation of state band has the form of two straight lines. So if you just, especially if you look at this subconformal equation of state, you can obtain this dark blue band almost, not quite exactly, but almost by just continuing from this low density nuclear matter equation of state with a straight line all the way to somewhere around here, and then just changing the slope to a smaller one that is predicted by this PQCD result at very high densities. And if we add to this picture the predictions from viable nuclear matter models, so nuclear theory phenomenological models of nuclear matter that predict that even maximal mass neutron stars are purely hadronic, and that pass all the observational constraints, like they all sort of support 2 solar mass stars, they all pass these LIGO and Virgo 90% limits and so on, then we see that these nuclear matter equations of state, they don't bend, they just, oh, wasn't supposed to go that click yet. So what we can see is that all of these nuclear matter equations of state, they just continue shooting up. They do not somehow have this bend that our interpolated equations of state appear to have. And this is, of course, very, very suggestive of something. This is suggestive of the interpretation that what actually is happening here at this kink or bend of the EOS band is a phase transition, that we actually go from the nuclear matter phase to the quark matter phase at around this point. And this is further sort of supported by the realization that if you plot the sort of critical region where we know that the deconfinement transition happens at high temperatures in quark gluon plasma, when one goes from hot hadron gas to hot quark gluon plasma, then one ends up with an energy density interval that is not terribly far, at least, from this kink that's taking place somewhere around here. And now one further thing to recall here is that this kink that I've been talking about, or the slope of this EOS band here that I've been talking about, this actually has a sort of, this is a well-known quantity in neutron star physics. This has a name, it's the polytropic index. It's the logarithmic derivative of the pressure with respect to the energy density, and we can go on and look at what values this quantity obtains. On one hand, in nearly conformal quark matter, there it can be seen to be almost exactly 1, and on the other hand, we can go and see what values it gets in sub-saturation density nuclear matter. The answer is about 2.5, between 2 and 3, typically around 2.5. So now this is all very suggestive, but not really quantitative yet. So the obvious questions that arise are, first of all, whether this two-slope structure of the EOS band is only a property of the band, or whether it actually persists when one starts to look at the interpolated equations of state one by one. And also, it's kind of not clear from these figures that I've been showing to you whether this is only a feature of the low speed of sound equations of state, or whether it also holds for those interpolated EOSs where we allow very large values of the speed of sound, even close to unity. And then, of course, the second obvious question is, where do the centers of different neutron stars lie? Do we have actually neutron stars that go where the centers lie to the right of the bend, to where we seemingly might have quark matter, or whether they are all below it, so that we would only have hadronic matter? And these are the questions that we plan to investigate, or planned to investigate, in the following way. We first went to generate a very large ensemble of viable equations, of interpolated equations of state, using this speed of sound interpolation method and allowing both first order phase transitions and arbitrary latent heat. And then we went to quantitatively compare the behaviors of the three physical quantities: this polytropic index gamma that I already talked about, the speed of sound squared, CS2, and then the pressure normalized by the pressure of a system of three quarks, the Fermi-Dirac pressure. We compute all these quantities in all of our interpolated equations of state and then compare their behavior to all these hadronic available viable hadronic equations of state that we have been able to find. And finally, we will try to identify some kind of an approximative criterion for the onset of quark matter inside neutron stars that would then allow us to ask quantitatively the question how much quark matter we have in different types of neutron stars, and under what conditions do we have quark matter, under what in for instance maximally massive stars, and under what conditions are all neutron stars in existence purely hadronic. Now, to answer these questions, I have to show you a very complicated looking three-dimensional plot. This is doing exactly what I claimed. This is a 3D plot where the axis, the vertical axis, is the speed of sound squared, and the two horizontal axes are the pressure normalized by this Fermi-Dirac pressure and the polytropic index going from 0 to 6 here horizontally. And in this figure, the thick black lines are the different viable hadronic equations of state that we have been able to locate, and the thin gray lines are then our interpolated equations of state, or actually not quite all of them in this figure, because this would become kind of very messy if we had all of our several hundreds of thousands of equations of state. Here we have a couple of thousand, but these are a representative subset. We have chosen these interpolated equations of state in such a way that they sort of fill all the volume of this cube that is filled by our entire set of equations of state. What is also shown here are these blue diamonds and then red circles or dots, and the meaning of these diamonds and dots is that these blue diamonds correspond to the centers or central densities of ordinary pulsars 1.4 solar mass neutron stars obtained either from our entire ensemble of viable interpolated equations of state, or these are the solid dark blue diamonds, and then these sort of cyan empty diamonds correspond to these nuclear matter equations of state. And here clearly there's a very good overlap between these two ensembles. There's sort of no reason to expect that sort of the neutron stars built from our interpolated equations of states would not be hadronic at these densities. But then when we go to maximally massive stars, so those neutron stars that are so heavy that if you sort of perturb them even slightly, if you increase their masses even a little bit, then they would collapse into black holes. In this case, there's something completely different happens. In this case, we in practice have absolutely no overlap between the ensembles obtained from our interpolated equations of state and from these sort of hadronic matter nuclear equations of state. So this 3D figure may be a little bit difficult to sort of comprehend, but then these two figures are two-dimensional snapshots, so projections into planes spanned by the pressure and the polytropic index, or the speed of sound on the right and the polytropic index. And here this sort of separation of the maximal mass central densities from these two different ensembles of equations of state is very clearly visible. So what at least I would take from here is that while 1.4 solar mass stars appear be composed of nuclear matter. At least there's no contradiction between the predictions from nuclear theory and this model-independent interpolation calculation. The same is not true for maximal mass stars. And in some sense, this figure here is our main result. Now, to move forward from here, one can also sort of notice that if one had to boil down the criterion for what is quark matter, what is nuclear matter, to one single quantity, then using the sort of average polytropic index between the 2.5 value that's obtained in low density nuclear matter and unity that's obtained in high density quark matter, meaning 1.75, using this as the dividing line, one is probably not making a huge error. So I have to emphasize at this point that this is only a very approximative criterion for what what we call quark matter and what we call hadronic matter. We don't mean to suggest that this gamma equals 1.75 is the exact physical criterion for the onset of quark matter, but at least on this sort of hand wave level, this is probably not a terribly bad approximation, and this crucially allows us to ask the quantitative question: how much quark matter there is in different types of neutron stars. So using this criterion, what we see is, first of all, that almost all interpolated sort of allowed equations of state for neutron star matter lead to the presence of quark cores in maximally massive stars, and these cores are even quite sizable for assuming that the maximal value of the speed of sound does not exceed 0.5, or the speed of sound squared does not exceed 0.5. So in this figure, I'm showing the size of the quark matter core in kilometers and in solar masses, assuming again these same sort of maximal limits for the speed of sound squared. And another question we may ask is what does it take in order for all neutron stars to be composed of hadronic matter alone? And the answer is that purely hadronic equations of state are viable only if the maximal value of the speed of sound squared is above 0.7, so that the speed of sound really reaches values fairly close to unity, and the deconfinement transition is first order. So in particular, if we knew, for instance, that the deconfinement transition was a crossover, there was no critical point on the phase diagram of QCD, then we would all automatically know that irrespective of how the speed of sound behaves, there are stable quark matter cores in the most massive neutron stars in existence. And finally, I'm almost done. I know that I've taken up almost all my time. So finally, I will also mention that while we did not use this sort of electromagnetic counterpart limits or the sort of simultaneous mass radius measurements that I mentioned earlier as inputs in our calculation, we can note that all of them are actually in perfect agreement with our subconformal equations of state. So while again we certainly don't claim that the speed of sound has to be sort of bound by this conformal value 1/√3 from above, but we merely note that sort of this equation of state band, the dark blue band, obtained assuming that the speed of sound squared is always less than 1/√3. This leads to very sort of nice predictions for the equation of state and the mass radius relation of neutron stars that are in agreement with all known robust observations. Good. So this brings me to the end of my talk. I will just want to remind you at this point that in the beginning of my talk, I asked these three questions. Can we QCD theorists predict the equation of state and the neutron star matter or the neutron star mass radius curve? If not, can we infer the equation of state using astrophysical observations? And does deconfined quark matter exist inside at least some neutron stars? My answers would be the following. For the first question, the answer is unfortunately negative. We are not able to just use particle theory and nuclear theory machinery to predict the equation of state and the neutron star mass radius curve yet. In order to do this, we would need some really fundamentally new machinery, like being able to solve the sign problem of lattice QCD or have a gravity dual of QCD, which we certainly don't have yet. But for the second question, the answer is much more positive. There has been a lot of progress recently with this sort of reverse engineering the equation of state, and the uncertainties are reducing. And finally, while we do not have a definitive answer for the existence of quark matter, I would say we have very promising sort of early results. And based on what I've shown you, I hope that I have convinced you that somehow the idea that maximally massive neutron stars might contain quark cores, it at this point should no longer be considered some kind of an exotic and very unlikely scenario, but rather the standard scenario. Thank you.
Thank you very much. There were a lot of questions in chat. I would like first to see if anyone wants to sort of say a question in voice. If you can unmute yourselves. And then...
well, I could ask a question.
Sure.
Related to something near the end of the talk. So for a all hadronic to have an all for all neutron stars to be made of just hadronic matter, how strong would the first order phase transition have to be? Can you quantify that by any chance?
Yeah, of course. So so it does not. So there are actually a couple of things I should mention here. So one is that even if we look at sort of very high the equations of state where the speed of sound reaches a very high value, we still at that point the majority of the equations of state we have generated predict quark matter cores. It's only a very, very small minority, something like a few hundreds of equations of state out of 500,000 that don't contain any quark matter at all. But then when we look at these few samples that predict purely hadronic stars, then actually the sort of minimal value of the latent heat is not very large. The order of magnitude is something like 150 MeV over Fermi cubed, which is quite a lot smaller than the sort of one proton or neutron mass per Fermi cubed. So in practice, you don't need a very strong first order transition, but you simultaneously need at least sort of a moderate first order transition plus the speed of sound reaching very high values.
Thank you.
I actually have a follow-up because I saw that Aleksi also asked about 2 first order phase transitions. So can you say anything about quarkionic matter?
This has been sort of on the list of projects to do for quite some time. So I don't at this point want to make any definitive statement. So from what I've understood about quarkionic matter, it's something that's very well defined in the large NC limit, but then it's less clear what happens when one comes down to NC equals 3. And this is a very I'm not sure whether we will be able to make any sort of quantitative statements about quarkionic matter, like how to identify it, for instance, in this interpolation calculation. The whole point of this interpolation approach is to sort of circumvent all the problems of microscopic calculations that one typically encounters in this close to the deconfinement transition. And it may very well be that in the end we won't be able to say much about these kinds of very detailed microscopic interpretations, but this is something we have not looked at yet in any detail.
My understanding is, I mean, from the last and from the last talks of Larry and also from my own, I worked a little bit on quarkionic matter, is that sort of the closest to the definition that you guys have is that pressure with respect to density suddenly jumps because it starts depending on NC. So it's a jump of a factor of 3 or so. Pressure with respect to energy density.
Okay. Yeah. So I mean, of course, well, I mean, first order phase transition typically has a jump in energy density, but the pressure is continuous. So when one considers these quantities as functions of chemical potential or not, varying chemical potential, the pressure is continuous, but the energy density jumps. But I mean, I would have to look at this in detail how to actually do it. So there are of course this other, like this second generation of stars, hybrid stars also that we haven't had time to look at yet, that it would be a very interesting thing. But yeah, so there are many projects that we simply have not been able to pursue yet.
Okay, we have a huge line here forming. Manuel has a question. So let me, then Fernando Navarra. Let me unmute Manuel. I don't know, you can unmute yourself.
Okay, sorry, I was looking for my microphone. Yeah, I have a question. My question is really, I don't really understand very much here why the polytropic index is important. Because we know, as you said, that polytropic index is, if it was really 1/3, okay, or something like, I don't know, in this line, pressure with the energy density, log, if it's a polytropic equation of state, it will be a line, okay? Okay, it will be just a straight line, okay? Okay, so in fact, for P equal 1/3, that, as you know, is because we are talking about the free quarks, okay? So free fermions, okay?
Yeah.
So the equation of state is linear with the energy density. Gamma is 1, okay?
Yeah.
As you wrote here, in fact, in your talk. So I don't understand very well why, because I understand if you think that you have a polytropic expression for your equation of state for hadronic matter, okay? In that case, I understand why gamma is important, but I don't understand very well why these two things should be related, because the sound velocity, of course, is related with gamma times P over E, but if it's a polytropic. So what is the idea here where you're trying to convince, because I have already many times ago, right, an equation of state that is P equal E to the power of 5/3, okay, that is 1.75, okay, more or less, okay. And so that was a good equation of state for nuclear matter, but we could not reach masses above 1.5, okay. So I cannot understand how you can really maintain this gamma as 5/3, let's put it that way, 5/3, and already and say that you have 2 solar masses. They're a little bit difficult for me to follow. So could you explain me more or less what is happening here?
Yeah. So so there.
So why gamma is important? Why is gamma?
Sure.
Gamma, the continuous gamma, if you cannot reach to solar
I understand your question.
The hadronic equation of state with the power of 5/3, let's put it that way. Gamma 5/3.
Sure.
What is?
So first of all, this kind of our fixation on gamma, so to say, is really it's mainly due to
come from your calculation. I understood. In fact,
So the reason why we are talking about gamma so much is really related to this observation. It was sort of one of our main motivations originally, historically, what was the observation of this change of slope in the equation of state band, and this is actually one doesn't even need any input from PQCD or from the Quark Matter side to see this kind of a slope. This is if you just extrapolate the nuclear matter equation of state and then take into account astrophysical conditions and causality and stuff like this, then you kind of this bending is inevitable. So what is sort of almost our main point, I dare say, is providing a physical interpretation for this bending of the equation of state that is happening. So we wanted to see how sort of whether this happens sort of individually for all the interpolated equations of state, or whether this is just some kind of a property of this band that kind of fools one when one is staring at it too much. And then we sort of we wanted to combine this sort of ab-initio information that we had from low densities and high densities, where we really know what values gamma obtains, and what really struck us as very convincing was that when you take go to Compose or any other repository for nuclear matter equations of state, and then just take all of those that are tabulated and that pass these sort of observational constraints, then then what you see happening is that all of those nuclear matter equations of state that somehow predict smaller values of gamma than roughly 1.75, they are thrown out. So what remains are only these sort of almost linear ones. And at the same time, at high density, we have this very, very crisp understanding of why gamma has to be close to 1. That has to do with the symmetries of the decomposition.
Yes.
And so in some sense you could say that this is sort of an observation that that actually for the vast majority of our so we have these few points here that where our interpolated equations of state have gammas of the order of 1.5 to 1.75 in the centers of maximal mass stars, but somehow the vast majority of our equations of state, they actually are very close to gamma equals 1. And this is sort of, I don't want to sort of I don't want to oversell our results. We don't claim to have discovered quark matter. We're just sort of showing evidence, showing suggestive evidence for why it might be there, and this is for from these observations that we've made, it seems that if one had to choose one single quantity to make this sort of phase identification, then gamma appears to us to be the best one, or the most efficient one.
Okay, thank you very much.
But yeah, this is a point that I want to really emphasize, that some of the stories that were written in media about our work were kind of overselling this point. So we have not discovered quark matter. There's actually one of the most important quantitative findings that we made was being able.
Yeah, I see. I should say for you one thing that I always thought, okay, and I'm still thinking, okay, that the fact that you have a very high sound velocity in the hadronic matter, and after you go to 1/3, is exactly because you have a first order phase transition, and you have a sound velocity does not need to be continuous. Only if you have one.
Absolutely. Yeah, no, there's no.
It's too hard to push that the sound velocity needs to go down. I don't know. That's my opinion.
Yeah, there's absolutely. Yeah, let me just quickly. Yeah, let me quickly respond to this. So there's, of course, I mean, we know very well what happens in a first order phase transition, and this is sort of. This is almost like the standard picture in the field, that there is a strong first order phase transition. The speed of sound first reaches something like, well, close to 1, and then it jumps to, and then it jumps very low and starts increasing again. This is certainly, I mean, this is a viable possibility. We have quantified.
This is what we have in hybrid stars. Okay, if you have an hadronic matter, and after you have a quark matter with some models of this. So this is known for
and this is by far not ruled out.
If it is a crossover, if it is continuous, so in that case, it will be a problem. In fact, in my opinion, because the only way is like you said that you get one cert and you continue with one cert forever for some velocity. It's the only way I see that would be a crossover, but I don't know. At least our nuclear neutron stars until now are indicating that the phase transition at high density and low temperature needs to be first order. Okay, not the other way around. I don't know. That's the way I think. Okay.
Sure.
Until now, two solar masses indicate these things. Okay, because I should tell you one thing that for you to know that I don't like too much about many of these plots of M over R. Okay, I am a nuclear physicist. This M over R, each one has a central density, and you can never show curves with M over R without showing M over central densities. Because if you have a central density of 7 times nuclear matter, you are not going to believe that you have hadronic matter. So this is very important, and people forget. So I saw a lot of plots of LIGO that when I see the central density is 5 times nuclear matter, and they are using an hadronic equation of state, that don't make sense. So you have a microphysics here. Okay, is the central density, and you can never forget that. But many papers show unrealistic hadronic equation of state being used up to 7, 6, 7 times nuclear matter to achieve 2 solar masses. Have no sense, in my opinion. But I don't know. So I don't know. I should tell you that thing that many times only the curve M over R is not enough. Okay, it's important to show the other one to see if it is reliable or no. I think you have thought about that. Okay.
Yeah, absolutely. And I really want to emphasize that we are by no means claiming that this kind of a scenario where you have a strong first order phase transition and the speed of sound reaches a high value and then drops. This is by no means ruled out. This may well turn out to be the case, and it's possible that then we don't have any quark matter. I mean, if you believe this to be the case, then it's only please can I?
You have a quark matter and you have a first order phase transition, yes? So you have a quark matter. So we don't know it seems that quark matter at high density, the equational states we have from our models are not stiff enough. They are not good. MIT back model, Nambu model, they are not good. That's what I think. But okay, so thanks for your attention. Okay.
Fernando, please. Sorry for the confusion. There's a lot of people. Yeah, Fernando.
I'll be very brief. So first of all, thanks for the very nice lecture, Aleksi. Thank you very much. Then coming back to theory, how solid is the assumption that we have a first order phase transition at 0 temperature and increasing densities? And then I just want to know more about the state of the art of theory in this respect. And also if one day it turns out that there is no phase transition, no first order phase transition, how does that affect all your conclusions in your results?
Yeah. Thanks. Yeah, this is a very, very good question. So this is a point where I think many nuclear theorists would disagree with me, but I have to say that I've never been convinced by the arguments that have been placed for there having to be a first order transition at small temperatures. And this is certainly a viable possibility. We are not saying that this could not be the case, but if one goes back in history, then before it was discovered that the deconfinement transition is a crossover one at high temperatures, many people actually thought that it has to be a first order one based on different types of mean field calculations and so on. And it's not clear to me at all whether this is not happening also in this case. I mean, it's certainly possible. I wouldn't place a bet of any kind regarding whether a critical point exists or not. I mean, it's a viable possibility, but there's no really robust first principles argument for that. And if it so then the follow-up question was, what if we so here what would it imply if we knew that there was only a crossover? Then it would immediately tell us that there are Quark Matter Cores. Oh. Because a non-zero latent heat is something that we need in order to have only purely hadronic stars.
Okay, thank you very much.
Thanks.
Further questions of people who, Mileto maybe? If you have a question, please unmute yourself. Anybody else? Okay, if not, considering it's already pretty late for you, thank you very, very much. It was a really nice talk.
Yeah. Thank you very much. It was a pleasure.
Good night.
Good night or good evening to you guys.
Yeah, exactly. And see you in a couple of weeks.
Thanks.
Yeah. Okay.
Thanks a lot, Aleksi. Very good talk. Thanks a lot.
Thanks.
We have a, yeah. Okay. Yeah. Thank you. I'm stopping recording and